Okay, so this was realized after um, I finished yesterday, but I totally did not have any audio last time. So we have audio now, and I'm double
Okay,
checking. So
yeah, you can hear
this
that.
was realized. Perfect. Sweet. Okay, so I'm going to give a little bit of a recap of what we did last time. So I think we reviewed a total of one Anki card. And then I sort of brought things together for what I'm going to be doing over the next little bit. Right now, I've mostly focused on a procedural sort of education of calculus. And now I need to focus, I focus on the conceptual and I need to focus on the procedural now. So I'm going to be doing that. I noticed that I do have more resistance towards doing that. The conceptual was like fairly easy to slip into, but the procedural, like I think the past three streams I've started late, like you can tell that I'm avoiding it. So we'll see. I obviously don't think it's gonna be bad as it or yeah, as like this imagined conception would be. But let's go ahead and get in it. So let's see. Well, okay. So calculus. Okay. So yeah, let's just review these cards. I don't think I have much else to say. Yeah, I'm excited to get into it. I obviously the knowledge will come in a fairly similar manner as it did for the conceptual, as will the procedural, or it'll come in a similar manner for the procedural knowledge as it was for the conceptual knowledge. So I just have to kind of get in it. Noticing the experience of fear or some hesitation is good because it allows you to like recognize it and just like sort of push through it. It will fade. I've found fairly quickly when you're engaging with something like a topic or some complex thing. And so yeah, my best advice would be there would just like to start and go in. So we're gonna go ahead and do that. Okay, so these are the cards that I made last time. I actually still don't exactly know what these cards are. I just placed them in before I I placed them in before I had like grasped it because I think last time was shorter as well. So I think I actually might. Let's see, new. Okay, so we have use substitution. Okay, yeah, I think I'm actually gonna hold off on these until I guess would be next week. So I will like open the possibility that we might add some here. But yeah, so we'll start there, and I think I'm just gonna go one by one with the things I need to do. So I think finding limits is probably the good, like, I guess, yeah, we'll just start here and like go down. Yeah. So for evaluating functions, I think I will eventually, or rather, eventually I'm interested in probably using something like LaTeX to display like the step-by-step of solving the problem. I don't super enjoy because I'm looking for a good experience when I'm going through step-by-step, and writing it out, like, this is really slow personally, at least I'm a slow writer, and I can type much faster than I can write. And then additionally, like you sort of begin to get all wonky with, begin to get all wonky with like, oh, like I'm writing something and it's creeping down to the right. Oh, and I don't know. So I don't want to deal with the handwritten stuff. I want it to look nice and like precise. And so I think I'm going to learn LaTeX for that. Additionally, I'm thinking about when I will be solving like these problems as part of like a daily practice and things like that. I just don't see myself using like a pen and paper. And so LaTeX again seems like the best option. There may be other things that are like better than LaTeX. So I don't know. But for now, from my cursory look, actually I want to see MathJax versus LaTeX. Oh, okay. Interesting. Okay, so maybe MathJax would actually work. Because I don't really need the document layout, right? Okay. Perfect. Yeah, so I guess we'll start here. I probably just want like a problem set on my right side. I'll move my Anki thing off screen. Finding limits, question set, problem set. Okay. Okay, so for limits, we're wanting to figure out what the output of the function approaches as this limit is approached. So I think we'll have an Anki card for computing limit because I remember there was like a few approaches. I think direct substitution can work. If you algebraically pull out, or let's see, if a direct substitution doesn't work and it's like yeah. So I'll give an example. So I think it's I'm in eraser mode. And I'm going to move this so I can see. Okay, and we'll just kind of scoot this guy over. Oop. No. Okay. Did not like me doing that. Okay, perfect. So, what we'll do here is... so X, oh my heavens, I'm still in the eraser. Okay, X, it's probably too big. X, let's see, I think it was X squared minus 4. And this was X minus 2, right? So if we, in this situation, I think it was something like the limit here was X approaching 2. So if we put 2 in here, then it explodes because we divide by 0. And so what we do instead is we factored out. Well, let's see. So limits are about what the thing approaches. So direct substitution would be the best way if it works, I would assume. Actually, yeah, let's just... Okay, so because if direct substitution works, that means as we approach 2, it's going to hit that number, right? So only in situations where we don't use direct substitution do we need to rely on anything else but direct substitution. That may prove troublesome, but I'm pretty sure that's reasonable. I'll erase the screen here. Okay. So starting with this one here. So that's 8 minus 3x plus 12. And I might actually be like... Is there a way to move this thing? No. Plus 12x squared. I might be able to get through limits pretty quick if that's the case, which I think it is. Okay, so that would be 8 minus 2 times 3, which is 6. Or, yeah, 2 times 3, which is 6, plus 12 times x squared, which is 4, so that'd be 48 here. And plus 2, so that'd be 50. Let's see if that was correct. Okay, it's 50. Okay. So, being that's the case, we probably just want to look for ones that are a bit hairier. Okay, so and by hairier, I mean which of these problems is going to have a issue with the direct substitution approach? So that'd be 5. So this one becomes 25 plus 10. Okay, so okay, I think I know the solution for this. So 1, or maybe not. This one I think will be tricky because if we see -5, that's 25 plus -10. And so this will be 25 minus 25. And so that will not be able to evaluate because it'd be 0 over 0. And so in order to calculate this, I think we could try factoring out, because x squared minus 25 is x plus 5 and x minus 5, right? X minus 5. And so I'm going to... Maybe the drawing is better because there is something... maybe for longer problems, LaTeX would be optimal, but for shorter problems, I don't know. It's like fairly quick. Well, but I don't know. I think I would still be faster typing this though. So I guess we shall see. Okay, and then we also have x squared. X squared plus 2x minus 15. Okay, now I have to remember how to factor this guy out. So obviously we're going to have x, and I think because there is a minus here, it requires us to have a minus. So we have x plus, x minus, x minus, and assume that we're going to, it's either going to be positive or -5. Oh, okay, I have it. Okay, so, okay, I think it's 5 and 3. Yeah, it has to be 5 and 3. And it is positive 5 because, okay, and then 3. So I'll describe how I got here. So I know that in order for this problem to be doable, or rather, because I know this problem set is not wickedly difficult, I know that it's likely the case that we're going to be able to do some factoring out shenanigans. And because of that, I know that I need either positive or negative 5. And so just kind of thinking through, so obviously x times x is x squared. For this, like 2x here, because when we like multiply these together, we're going to go here and here to, let's say we'll, here to here, here to here, here to here, here to here. Yeah, that's everything. Yep. Okay. So we're going to do all that. And so I'm going to have 5x and then negative 3x as well. And so positive 2x is the only like situation that we can get from there. And obviously 5 times 3 is 15. And so it's going to be negative 15. So that is the correct one. Okay. And then with that, that means I knock out the, oops, not with that. That means I knock out this one. And that leaves us with x minus 3. X minus 3 over x minus 5. Yes. And then now what we're going to do is just substitute negative 5 in. So it's going to be negative 5 minus 5. So that'll be negative 10 over negative 8. And so that'll be 10 over 8, which is 5/4. Let's see what we got here. Five-fourths. Perfect. Okay. Okay. I'm feeling pretty good about that. I think I'd like to do one piecewise function. I also want to browse to see if I have... Oh my heavens. Find? I don't know if I've... I wish there was a better way to search up an Anki. Find... how... Find limit. Find limit. Okay. Okay, we'll just add a new card since I'm not aware if I have it. Chat.openai.com. Okay, how do you find a limit in calculus? Less than 50 words. Okay. To find a limit, observe the function's values and input. As the input approaches a specific point, simplify the expression if needed, then substitute the point. If direct substitution fails, try factoring, rationalizing, or using L'Hopital's rule for indefinite forms. Okay. Okay. Yes. Factoring. L'Hopital's rule. Rationalizing is when in limits involve square roots, multiply the numerator and the denominator by the conjugate to limit the root and simplify. Oh, okay. Okay. So, process of rationalizing when finding a limit. in calculus. Okay. Reasonable. And then L. I think I just need to grab this because there's no way I'm going to find that character guy over the O. L. L'Hopital's rule for finding a limit in calculus. And differentiate the numerator. Then take the limit of the new fraction. Repeat until the... Interesting. And would differentiating be done using the power rule? Oh, okay, okay. So it looks like there's also product quotient and chain rules. Okay, so the limit laws, it's interesting why we have limit laws because, well, I don't know. It seems reasonable that you just evaluate the input or the input or the given, the limit input against the function to find what it's approaching. If we're saying we don't want to get to this limit, then like inputting it and evaluating the function seems like the reasonable approach. So I'm interested in why we have, yeah, I'm going to ask that question. When evaluating, a limit for a given function, why is it the case that we have limit laws, question mark? It seems fairly clear that if we are wanting to figure out what the output of the function will be as it approaches the limit, that we could just substitute the limit input into the function and then evaluate it, period. Could you describe some reasons for why this is the case or why it might be? Oh, okay. That makes sense. So it is the case that it's obvious for the input and output, but for situations where we have this right here, you do want to formalize how you're able to use or how you're able to evaluate limits. So that the fact that I can do this is important. Okay. Okay, that makes sense. Okay, I think we can move on. Okay, so next I would like to... Oh, nice. Okay. So this one we're evaluating for a particular limit. Evaluate the limit here. Okay, this seems straightforward again. So for piecewise functions, we just input it. And so if x is -6, that means that we follow this function here because x is less than 1. And then so we do -6 times 4, it should be 24. Yeah. Yeah, 24. And then plus 7, so that would be 31. And then 1 would be this one, so it'd be 3. 31, 3. Perfect. Okay. I'm feeling way more confident in getting these limits done. Okay, I don't know what the squeeze theorem is, so we should do that. Oh, I also want to figure out L'Hopital's rule. That's fine. When finding the limit of a function, what is the use of the squeeze theorem? Ba-ba-dum. Squeeze theorem helps find limits when a function is difficult to evaluate directly. If the function is squeezed between two others that share the same limit at a point, then it must also approach that limit. Huh? Okay, so I'm going to add this. Because this is a slightly different question. This is a little bit more about the application of the squeeze theorem. But now I'm going to have one that just flat out says what is the squeeze theorem in calculus. Oh my heavens. States that if f of x okay, if f of x is less than or equal to g of x and g of x is less than or equal to h of x near a point, and limit x to a, f of x equals limit x to, okay. Then L, where's oh, okay, so we're like burning it up. So this is G is equal to L here, right? And if we say f of x, x to a is equal to the limit. Okay, so that we're saying the limit of this function is equal to the limit of this function and equal to L. Then that means the limit of this function also equals L, because we're saying f, the limit of this function, and the limit of this function, limit of this function and the limit of this function are equal, meaning they're this guy L here. And then that means the limit of this function also equals L. And the reason being is that I think we're just we're merely saying that these are actually equivalent. Because I don't know if you can, well, what do we mean like f of x is less than or? Because if the limit, well, actually no, that's not true. I'm not sure what we mean here by having a function less than or equal to another function. It makes sense for values, right? Is it the evaluation of the function? Do parentheses necessitate or guarantee evaluation? I am not sure. Okay. I don't have an intuition for what it means for a function to be less than or equal to another function. Could you describe that? Oh, okay. Um, okay, so I'm saying, what does it mean for a function to be less than or equal to another function? Probably should have zoomed in here earlier. Oh, heavens. Okay. Okay, I think we are going to, well, let's see. So, yeah, I think we'll probably wrap up here. I think this is a great site here. This is pretty sick. So, yeah. I think we'll end there. We're learning about squeezed functions. I was happy with the fact that we were able to step through limits quickly. I hope the speed continues. If so, then we'll be able to complete the MIT Cumulatives exam in no time. Okay, well, I will see you guys later.